Today we're going to look at a more complex technique of integration. So far we've really talked about how to integrate functions that integrate directly. We haven't talked about any of the more complex types of integration like we did with derivatives, where we had product rules and quotient rules and chain rules and all of those things that describe relationships between functions. Much the same thing exists for integration. We'll only study one of those more complex techniques. The other ones are typically covered in a second semester calculus course, and so you would see those if you continue to take calculus next year in college. So today we're going to look at the only one of the techniques of integration that we'll have that will talk to us about how to undo a derivative that came from a more complex process or from two functions or being considered together. And substitution undoes the chain rule for us. And so we're going to remind ourselves how the chain rule works, and then think about, well, what would we need to identify, and are there easy ways to identify those things in order to go backwards? If I'm being asked to integrate something that is a chain rule derivative, how do I reverse that derivative process in order to integrate? So let's remind ourselves of what the chain rule really tells us. So here we're being asked to find the derivative of y equals sine x squared. Remember that if I need chain rule when I have the composition of two functions. I remember the outside piece is sine x and the inside piece is x squared. And I remember that in order to find the derivative, I need to find the derivative of the outside. The derivative of sine is cosine x squared, leaving the inside function alone, and then go back and multiply and find the derivative of x squared. The derivative of x squared is 2x. So before I move on here, I want to notice some things since I'm going to have to reverse this process. One of the things I notice is that the original function is a single composed function. The derivative has two pieces, a product of two pieces. So when I'm going in reverse, I'm going to lose something. I notice that the thing that I lose here is the derivative of this inside, what I've normally called g prime, and g prime goes away. If I'm looking from the derivative back to the original, I don't see this derivative, the derivative of the inside piece, anywhere in the original. Also, if I compare this original original part of the derivative I have here, so this is f of g prime, I notice that if I compare it to the y equals version, then cosine would be integrated back to sine, but x squared stays the same, so the inside piece of that remains the same. I remember that the chain rule tells me to do the derivative of the outside, leave the inside alone, times the derivative of the inside piece. In words, the result of applying the chain rule is the product of two factors, and we've just said that it's the derivative of the outside, leaving the inside, times the derivative of the inside piece. So again, when we're going backwards, what we notice is that g prime disappears in the integration, and that f prime returns to f, and that g of x just passes through. That it's on the inside in the original, that x squared is there in the original, that x squared is there in the derivative function. Okay. So we're going to talk about two strategies for finding the antiderivative. One thing you can do is just guess and check. And so you can notice what you believe is the derivative of the inside piece. Know that that disappears in your integration. I only need to integrate the outside, and so I'm going to integrate that, leave the inside there, and then check to make sure that if you find the derivative of your answer, you get the question. I am going to focus on the more formalized process known as substitution. Guess and check is very difficult when you first start learning how to find these integrals, and so substitution is a good tool, at least until you get used to it. Substitution is a more formalized method that involves making a substitution for the inside piece, the inside function, results in a simpler function to integrate. We then integrate and reverse the substitution. So the substitution is actually temporary. The goal for substitution is to make it really clear which piece disappears in the integration, where's g prime, and making it disappear, and then allowing us to focus on the function that we need to integrate. So where's my outside function, and what do I need to do to integrate it, and then leaving the inside alone. So it reduces the complexity of the integral down to something that involves very simple functions and variables. So we get rid of a lot of the complexity with substitution. We're trying to make it easier, an easier integral to evaluate, and then once we've done the integration, we undo the substitution. The interesting thing with substitution, and I'm not sure why this is that rather than sticking with our convention of g prime and g, we switch to u, maybe just because I don't know why. So u is going to now be my inside function. So the thing that in former notation I might have called g, and du is the derivative of u in terms of x. Let's do an example. So here I see I'm being asked to integrate, and the way I know I need substitution is, for one thing, I see a very complex integral. I see multiple functions. This is the first time I've seen that. The functions are multiplied. There's my multiplication, 3x squared times cosine x cubed. When I see that level of complexity, I should suspect that I need substitution. So I'm going to identify the inside function. So what I want to do is think of, okay, if I'm thinking of chain rule, then one of these two functions is still a composition. It's f prime of g of x. And the one of these that's still a composition is cosine of x cubed. So there's my composition, my composed function. I want to let u be the inside piece of that composed function. So, and I'm kind of used to that notion of outside and inside, so u is going to be x cubed. Once I've made that decision, then I'm going to do some algebraic work or some calculus work with u and x cubed. I'm ignoring this original integral for the time being. I'm over here kind of working on the pieces I need in order to set up my substitution. So I'm ignoring everything that's going on with the integral, and I'm just finding, once I've set up u, then I'm going to find the derivative of u. So the derivative of u in terms of x, du dx, is 3x squared. Then I'm going to solve for dx. And the reason I solve for dx is because dx is in my original question. This u and du business is not there. And so I'm going to solve for dx. If I solve that little equation for dx, I know that du equals 3x squared times dx. So dx is 3x squared, no, that's wrong, is du divided by 3x squared. So dx is du divided by 3x squared. When I substitute, I always substitute my original choice. So I make the trade out for u, and I always substitute for dx. So those two. So I'm going to make those substitutions. 3x squared stays there. It's not one of the things I'm substituting. Cosine stays there. X cubed is one of the things I'm substituting. It becomes u. Dx is one of the things I'm substituting. It becomes du divided by 3x squared. So again, the only things I'm substituting for are x cubed, the original choice, and dx. So the inside piece in dx. Then I'm going to simplify a little bit. Notice my 3x squareds cancel out. That seems convenient. And I'm left with the integral of cosine of u du. That is certainly much simpler than the integration problem that I started with. I have clearly the function I need to, the only function that's here, the only function I need to integrate is cosine. The antiderivative of cosine is sine. U just stays there, plus c. And now that I've integrated, so I've found the integral of cosine is sine. Now that I've integrated, I'm going to reverse the substitution. Sine. Going back to that original statement, u was x cubed plus c. Now, students often ask me, what happened to du? Where did du go? Du didn't go anywhere. Du is the derivative of the inside piece. And remember, when we find the chain rule, we start with a composed function. Its derivative has two pieces, one of which is the derivative of the inside. So if we are reversing that process, then we're going to start with two pieces, one of which is the derivative of the inside, and then when we reverse it, we're going to lose that. We're going to go back to a single composed function. So du is the derivative of the inside piece, and the derivative of the inside piece never appeared in that original question. So I'm safe just to integrate the f function, the outside function, cosine back to sine, leave the inside there, and disregard the derivative of the inside, my du. I could check this to make sure I've done the correct integration. The way I check is by finding the derivative. The derivative of sine x cubed, the derivative of sine is cosine x cubed, times the derivative of x cubed, which is 3x squared. The derivative of my answer matches the original question, and so I've done that correctly. Okay, we're going to look at some examples, and actually I'm just going to do these three with you, and you should sort of follow along and make sure that you're understanding the process. And then tomorrow in class I have some more examples on the next slide, and we'll actually work through those. We'll talk through those and work through those. This section is more complex, so I'm actually expecting you to have more questions in class tomorrow than usual, and I know that we'll need to do some fill-in work tomorrow, more lecture, more instruction in the classroom, rather than you just working through a problem set. So let's work through these three and just kind of think along with me and make sure that you understand the process that I'm doing. So the first thing I check for to see if I need substitution, my first clue is, does this look like a really complex integral? Okay, I can do that really quickly. And then my second follow-up question is there a product or a quotient that I can't simplify just to be a sum or difference? So am I stuck with two things multiplied or divided? This one fits because there's nothing I can do to 2t times e to the t squared plus 1 for it to end up to be just a single function or the sum or difference of functions. So my multiplication sign is there, 2t times e to the t squared plus 1. I look at my two products, the two pieces of my product, choose the composition, that's this guy, and then the inside piece of the composition, that's t squared plus 1. There's the beginning of my substitution, is establishing the inside piece. Then I'm going to work through getting ready to do my substitution. So now I'm actually ignoring the original problem. I'm just working over here with u. So I'm going to find du dt. That's 2t. And then I'm going to solve for dt. When I do that, I can see that du divided by 2t is dt. Now I'm ready to make my substitution. I always substitute for dt and my original choice, my t squared plus 1. Everything else stays the same. The integral, 2t stays there, e stays there. T squared plus 1 is one of the things I'm substituting. It becomes u. dt is one of the things I'm substituting. It becomes du divided by 2t. Then I simplify. My 2t's cancel. So I have e to the u du. I still haven't integrated, but now the function, compare this to that original question, how much easier it is to integrate e to the u than the more complex thing that I saw originally. So I know the antiderivative of e to the u is just e to the u. Again, du disappears. It's the derivative of the inside. And I know that the derivative of the inside did not appear in my original function. It got there because chain rule expands things. Now I'm going to, once I've integrated, I'm going to undo the integration. The substitution. So u is going to return back. I'm going to trade u in, get t squared plus 1 in, and then plus my c. E is the only function that appears the same pre-integration, so behind the integration sign, and outside of it. So be really careful with that. Typically, when you drop that integration sign, you should be writing a new function there. E is the exception to that. Let's look at the second example here. So again, I see a product square root of x squared minus 2x times 2x minus 2. I have parentheses there even to draw my attention to that product. This is the function that's the composition, the square root of x squared minus 2x. I want u to be just the thing that's on the inside of that, so just x squared minus 2x. Then I'm ignoring the question, just working over here on the pieces I need to substitute. So du dx is 2x minus 2. So that means that dx is du divided by 2x minus 2. I'm going to make my substitution now. I always substitute for dx and u. So the square root of u, x squared minus 2x becomes u. Then 2x minus 2 stays. It's not on my things to be subbed out list. Dx gets changed. It becomes du divided by 2x minus 2. Then I clean things up a little bit. Those cancel. I'm going to rewrite square root of u as u to the 1/2 du. Now pause for a minute. Now that you've done all that work with your substitution, look how much easier this is to integrate than that long thing that you started with. Just don't forget to integrate. So now I'm going to integrate u to the 1/2 power. That's just a power function. So I'm going to add 1 to the power, divide by the new power. Dividing by 3/2 is the same as multiplying by 2/3. And then I'm going to reverse my substitution. I could check this quickly to see if I found the derivative of my answer. Would I get the question? I would, if I were finding the derivative of the answer, 3/2 times 2/3 is 1. So x squared minus 2x to the 1/2. Then I would come back and do the derivative of x squared minus 2x. So 2x minus 2, that appears to match what I had to start with. So I found the correct integral. Again, notice how well u masks the complexity here. U is this big long thing. U is what we used to call g. U passes through the integration. So it just comes through. The changes are made to whatever's going on with u, u to the 1/2, e to the u, cosine u. So u is just coming through, which allows the integration to be really, really simple. Okay, looking at question number 3, I'm pretty good at this by now. I see my composition is here. I see a multiplication that I can't simplify, so I'm going to let u be the inside piece. Then I'm going to find the derivative of that. Then I'm going to solve for dx. Now I'm ready to make my substitution with dx and for x to the 4th plus 5, my original choice, and my dx. So when I make that substitution, x cubed stays. It's not one of the things that gets changed. The square root stays. X to the 4th plus 5 is one of the changes, and dx is one of the changes. Canceling as I go through, I see then, and I'm running out of space here, so I see du divided by 4. I'm going to think of that as 1/4 times the square root of u du. I know that the 1/4 comes through in the integration, so I can just bring along 1/4. See if I can move it up a little bit. 1/4, and then I'm going to integrate u to the 1/2, so that is u to the 3/2. Dividing by 3/2 is the same as multiplying by 2/3, and I end up with 2/12, so 1/6 u to the 3/2. I've run out of space here. So we'll talk about this one again in class tomorrow just to make sure that you understand it all the way through. Let me see if I might be able to erase it and at least give you the answer so that you can see. No, I can't do that. So we'll finish up with that one in class tomorrow. So you should come to class. I expect that you'll have questions because this is a more algebraically complex process than we've done, and it's easy to lose what you're really doing, what you're trying to focus on. So make sure that you have your questions ready when you come to class, and then we'll do some more example problems before you start your homework. This is our last technique of integration, so we're just practicing from now on until your gateway these rules for integration or the techniques for integration. Okay, that's it for today.